2, 4. Okay, so Alma and Juliet not here. We had a test. It didn't go as planned, but it went. I posted scores for you. They're heavily discounted scores, let's put it that way. And after Leslie takes the exam, I will go over them with you so we can try to clarify things that students didn't understand for the learning experience. In the meantime, we will start talking about galaxies. So here's a picture of the Milky Way galaxy. Now, it's always important to make sure people recognize when you look at this picture what part of this is the Milky Way galaxy. And there's two answers that you can give depending on how specific you want to be. So what part of this is the Milky Way galaxy?
That yellow part.
Yeah, the little.
Yellow part of the bottom of the left. Okay, the two answers, all of it is one of them. Everything that's got, we're in the Milky Way galaxy too, so we don't have to cut out the Earth, but all of that is looking at Milky Way galaxy in the sky. There you go. And then the other answer is, whoops, I forget you have to change it with your finger. The other answer is this portion here. Now that portion there is where the vast, vast preponderance of stars and stuff in the Milky Way galaxy is. That's where the disk of the galaxy is. And so when you look there, you're seeing the light of literally millions or billions of stars combined to give you what looks like a cloud. And then you have actual clouds, if you will, nebulae that are blocking some of the light. But everything in that picture, well, I say everything. There are some things that are probably outside of our Milky Way galaxy. There are probably some other galaxies there. But when you look with the naked eye, everything you see is in our galaxy, except for the Andromeda galaxy in the northern hemisphere, southern hemisphere, you have the Magellanic Clouds. Everything else is in our galaxy. So we're going to be studying that. Now, the name to me is interesting. The ancient Romans called it the Via Lactea, which would be the road of milk. Because you look in the sky, you see this cloudy thing, and they say it looks like a road of milk. So that's Latin, the Via Lactea. And then we have the Greeks who called it Galaxies Kyprios, which, as I understand, means roughly the same thing, the Milky Road. And so we go with the name for our galaxy is the Milky Way, and of course, we call it a galaxy after the Greek word. So both of those, the Greek and the Roman names, are used here for the name of our galaxy and galaxies in general. So this picture here, when you look at the picture at first, you're really confused probably. What you're seeing is there's the horizon. So that purple line is looking out horizontally in all directions. And so here you have a tree that's in that direction. Looks like a power pole in that direction. Maybe another power pole there. And then you're seeing the sky above. And of course, the focus of this was not that. I just want to make sure you get your reference. The focus of this, again, is to see that Milky Highway, if you will, which is the disk of the galaxy. So our understanding of the Milky Way galaxy, we have ancient people saying it's a Milky Road in the sky. They knew there was something there, something to it. But they didn't know what it was. And so we go to William and Caroline Herschel, brother and sister team. He was a musician who's reasonably famous, moved from Germany to England, worked for King George, discovered Uranus, wanted to call it Georgius Sidurus or something like that, King George's star. But that was nixed because King George was not a god. Anyway, he and his sister did a lot of things in astronomy. And one of the things they did is they decided to try to map out the universe, I'm sure is what they were thinking. And so they looked at stars and they said, if we're just going to take the sky and break it up in pieces and count how many stars we have per unit of area in the sky. And if we see more stars, that means that the universe goes out farther in that direction, which is semi-reasonable. And so doing that, they came up with this map of what our universe looks like. The farther out, the more stars they saw. So that's really our first mapping of the galaxy. And of course, like I said, I'm sure they thought it was the universe. Now we go on, and we have Kapteyn's universe. Jacobus, or I'm sure it's pronounced differently, Jacobus or something. Kapteyn, he improved the model, and he came up with a model that was much bigger and shifted where we were in the universe, called Kapteyn's universe. Then we get to Harlow-Shapley. Now, we talked about globular clusters and open clusters already. Harlow-Shapley was looking for globular clusters, and he saw that there were a lot of globular clusters centered around Sagittarius. And so he said, Sagittarius must be the center. We're not the center of anything. Now, that's a reasonably large step going from the ancient Greeks saying that the Earth is the center of the universe to the Copernican revolution saying the sun is the center of the universe to now Harlow-Shapley saying neither is the center of the universe. Why the center of the universe is somewhere out there. And actually, it's the center of the Milky Way galaxy. I think by the time we got to Harlow-Shapley, he actually understood that it was the center of the galaxy. So he did it by studying globular clusters. And by using the Cepheid variables, he was able to calculate a distance to different things. And so he was able to get a more accurate distance measurement. Not accurate, but more accurate. So here's a lovely picture of Harlow-Shapley and some comparison to his model, and the little black there is what the Herschels came up with, William and Carolyn Herschel. So you see his galaxy here is much bigger than theirs and has a soft center. Here is what we believe the galaxy looks like today. Now, keep in mind, every picture I show you of the Milky Way galaxy, it's not a picture of the Milky Way galaxy. It is an artistic rendering, because where would you have to be to take a picture of the Milky Way galaxy? Outside of it. We can't even get outside of the solar system, much less the galaxy. So this is a calculated picture of what the galaxy looks like. The first one's a top-down picture. And you look at that top-down picture, and you notice it has the sun marked. You are here. Okay, I'm going to change to yellow. You are here. That is called the Orion spur, that little line that we're on. Now, what are these lines? These lines are regions where there are lots of stars. So if you look down, you see these stars. Why would they call this a spiral galaxy? A dumb question, not some hard to answer question like the one on the test. Because it's all spirally. Now, it's actually called a barred spiral. Barred because the nucleus, the center, is shaped kind of like a bar. So this here, notice it says nuclear bulge, and you look here, it says central bar. This here is the bar. So using my yellow again, I'll draw in the central bar. Maybe I should have gone with the purple there. Yeah, you can see it. That, for once, you can see better up there than on my screen. So what we have is a barred spiral galaxy. And then we have those spiral arms. How many spiral arms do you count?
4 plus the spur.
4 plus the spur. That's what I count too from this picture. So it's all of these things wrapped around, so it seems like there should be more. And you'll notice that the Carina and Perseus arms come from one side of the bar, and the Cygnus and unnamed on this graph arms come from the other side of the bar. This is a top view, and this is a side view. If you just looked at the galaxy like this, you would say, well, that is just a flat galaxy, kind of like the Earth, right? Right, Alex? Yeah.
That's hilarious.
Well, somebody thought it was hilarious behind you.
No, just the fact that you're catching on to my joking instead.
Yeah. I know you don't believe it, Alex. Okay. This here is looking at the side, and what we have is a pretty flat disk with some stars out there. The vast preponderance of gas and stars are in the flat disk, but we have some on the outside. And notice we have a measurement from both pictures of how far we are from the center of the Milky Way galaxy. It says 26,000 light years, or around, that works perfectly on the white. Around 8 kiloparsecs, if I remember my numbers right, is the distance from the center of the galaxy to where we sit. And at this point, it doesn't matter if I say the center of the Earth, because what's one astronomical unit compared to, 26,000 light years? These are actual photographs, not of the Milky Way galaxy. These are photographs showing two different types of spiral galaxies. One has a bar, one doesn't. Quick, which one has a bar, A or B? B. B has a bar. B, and of course, I'm no longer with yellow, but I think red will stand out. B has a big stinking bar there. Actually, if you look at it, it looks kind of like it has a bar like this and then a smaller, fainter one like that. But I'm going with this. So that clearly has a bar. Whereas this one here doesn't have any signs of a bar. I have read some people speculate everything has a bar. It's just some of them are so small that we don't recognize it. Question, Alex.
What causes the bar?
That's a really good question. I don't know the answer. I know. Fulfilling, isn't it? So these are spiral galaxies. Notice another difference here. This here is not very tightly wound. This one here is more tightly wound. And so we have differences in galaxies and how tightly wound they are. In fact, spiral galaxies are labeled either S or SB, the B for bar. And then after that, they're labeled A, B, or C for how tightly wound they are. So you have an SA, SB, and SC, or SBA, SBB, SBC. So notice if it's SB, it's a barred spiral. Or it's not a barred spiral, it's a spiral that's intermediate in winding. I just put this picture in because A was in the textbook, and B, it's a really great picture. What is this? What is the main feature of this? I say, what is it showing? Of course, you say, it's the Milky Way galaxy. What's the main feature you see here? Okay, it's the bright thing in the middle is the main thing you notice. And then you notice some structure on this kind of interesting. Now, all of that light in the middle, it looks like it's, a nebulous light spread out everywhere. But it's just, a million points of light all combined to look like a spread out light. So that is the light of, like I said, literally millions or billions of stars that's making it look just like a glow. And then the dark thing that Mira was pointing out, that's gas that's absorbing light from behind it. Yeah.
So then the thing that looks like there's something in the middle that's just the light of. I'm talking about the middle here.
The middle horizontally? Or
No.
vertically? Vertically.
Yeah, horizontally, we can say that. Yeah. I'm saying that that particular middle has more light, right in the middle of that part. It's just the light of the.
It's just there's more stars in that direction.
Okay.
So, if you actually plot the stars, Walter, I'm going to pronounce his name Body, although, his first name's probably supposed to be pronounced Walter or something. He observed something kind of weird, that the stars that are in the disk are fundamentally different than the stars that are not in the disk. Not in the disk we call the halo. So the halo is the region that's going above and below the disk. it's like when we were talking about our solar system, we had the Oort cloud and the Kuiper belt. The Kuiper belt is extending out from the plane of the solar system, and that would be the disk region going from the Kuiper belt in if we were using galaxy terminology. Whereas the Oort cloud would be the halo for terminology comparison. So we noticed that there were different types of stars. The stars that were in the disk, you had lots of O's and B's. Well, lots of. You had a fair number. O's and B's are very, very bright, hence easy to find. But they also have short lifetimes, as we learned in the previous test material. So where you have O's and B's, you have stars that have been formed in the recent past. Recent now meaning within the last, million or 10 million years. So we have fairly young stars in the disk. The stars that were in the halo, though, no O's and B's. Only the stars that have long lifetimes. And so he said, these are two populations, two different ages. The disk has the young stars that he called population 1, like the 1-year-olds. And the halo has the old stars he called population 2, 2-year-olds or older than 1-year-olds. And so we have these populations, population 1 and population 2. Now just to jump forward, the Cepheids have two types, the type 1 Cepheid variable and the type 2 Cepheid variable. The type 1 Cepheid variable are population 1 stars. The type 2 Cepheid variable are population 2 stars. So the different types are based on the types of stars they are. Now, I said old or young, right, for population 1 and population 2. There is a more classical definition than old and young. And that classical definition is the population 2 stars are primarily hydrogen and helium. Very little of the, quote, metals. Remember, to an astronomer, a metal is anything that's larger than helium. Whereas the population 2 stars have a higher percentage of metals. Or excuse me, population 1 stars have a higher percentage of metals. Well, where are the metals formed? How do we get anything that's bigger than helium in our universe? From stars, but more specifically, what part of the lifetime of a star? From deaths of stars. So population 1 stars are stars that formed after another star had died in its vicinity, so that it contains material from other stars that had previously died. They're recycled, if you will. So population 1 stars recycled material. Population 2 stars are more pristine material like was created in the Big Bang. There's actually a population 3 that's supposed to be, really super pristine. So that's the difference in the populations, and it tells us something then about how the Milky Way galaxy must have formed. We have only old stars in the halo. That means we probably used to have material in the halo where you could form stars. What do you need to form stars? You need a what?
Cold, dense cloud.
Cold, dense cloud, molecular cloud. So there must have been molecular clouds out there where there is virtually nothing now. And so if you think about it, the method we talked about for the formation of our solar system works perfectly well for the galaxy. That the galaxy was this big nebulous ball, and then something happened to make it start collapsing, and collisions made things flatten out into a disk. But the stuff that formed early into chunks was able to maintain its orbits. So here's just a comparison of the population 1, population 2 stars. Now, which one is population 1? The disk and concentrated in arm, or that's bad English. It should be concentrated in the arms, but anyway, which one is this? Is this population 1 or population 2? Right. Population 1 in the disk. So population stars are young, less than a few billion years in age. Now, is our sun less than a few billion years? How old do we believe the sun to be? about 5 billion years. The sun is not less than a few billion years, but at the same time, it's not greater than 10 billion years. It's somewhere in between those two numbers. But the sun is relatively old for a population 1, a disk star. There are lots of old stars in the disk, right? Because some old stars would have formed in the rotation plane that everything collapsed to, they would still exist there. So it's not crazy to have a star that might be a population 2 star in the disk, but it would be unexpected to find a population 1 star in the halo. Okay, the colors, well, because you have young stars, you have very massive O's and B's, those are blue in color, and they give off so much light they dominate. So the population 1 stars, it says blue overall because it's dominated by young stars. They're the supermassive stars, not just young. You can have a young M, but the supermassive stars dominate the light, so it's the blue overall. It's going to have all temperatures, all colors. Whereas the population 2, red, because they're all old. And only red stars can grow old. The bright stars don't have old lives. Orbits, the ones in the disk, are approximately in the disk and circular. Why circular? Why not crazy ellipses? What happens when you have crazy ellipses? You crash into each other. And what happens after you have enough collisions? You equalize until they're all doing circular orbits. Now, when I say collisions, it's very, very rare for stars to collide. But they can get close enough to interact, and that's going to still do the same thing, right? Gravitational interaction, slinging them about. Whereas if you look in the halo and bulge, you have them going in all kinds of crazy directions with really eccentric orbits about the center of the Milky Way galaxy. And then the final one, the one that's the technical definition, the heavy elements are about 3% in the population 1 and only, less than 0.01 to 0.01 to 0.001 for the population 2. So that's a very clear difference. So here's a picture identifying the different parts of our Milky Way galaxy. So we have the halo. We've talked about that. I hope this picture squares with the picture you had in your mind. We have the disk. Word I've used that I did not define is the bulge. There is what looks like a halo again around the center of the Milky Way galaxy. That's the bulge. And then you have the galactic center, of course, is at the center. I don't know what else to say. The sun, just somewhere out near the edge, actually. Apparently this was in here. I started with the textbook and went through. You can tell I've altered all of these slides except for this one. Somehow I skipped over it. I don't know what's going on here. I didn't see it. I didn't prepare. I've never talked about that one before. This here, though, I meant to have. This here is a great picture from NASA. I got to turn off the light so you can see the contrast better. That gives us as complete a look as we can have of our Milky Way galaxy. So here, once again, you see the central bar. There's the central bar. And then you have, what? It says the Norma arm is this little arm that none of us counted. And then it calls it an outer arm here for the same arm. The Sagittarius arm is this arm here, and that's the Perseus there. So the names are changing because that's where we see the constellations. Here's the sun. You can see all the lines are going out from the sun in the Orion spur, and then this here is the Scutum Centaurus arm. Those names are based on what we see when we look in those directions. So if you look out here, you're going to see Perseus. If you look here, or I think there, you're going to see Centaurus or Scutum. If you look here, you see Sagittarius. That's how we get those names. This is a picture showing where we are more precisely. So the sun is that. There's the sun. In that Orion spur. Now we see the Orion spur actually crosses basically from the Sagittarius arm to the Cygnus arm. Kind of hard for me to understand that. That doesn't follow a spiral pattern, right? I actually don't know what theories are. I'm just thinking about why that would be. And the first thing that comes to my mind is I told you before about the interaction between our galaxy and another galaxy, and we're in that place where it's crossing over. Maybe that interaction is what caused the star formation. I can't say. But it was interesting. I noticed this when I was preparing, but I didn't have time to figure that out. So here we already talked about theory on this, what it suggested. Here is the theory on how a spiral galaxy forms. You have two galaxies. See the picture on the left? Two galaxies. We call those irregular galaxies. They're flocculent, meaning like woolly. And if those galaxies interact, then fun things happen. Why would galaxies interact? Well, while stars hardly ever collide, galaxies have a space in between galaxies that's only about 20 times the size of the galaxy. Space in between stars is, millions of times the size of a star. So stars hardly ever collide, but the galaxy is only 20 times the galaxy size. They will definitely interact. And so I'm walking along, I've got that attraction to one person, so I get pulled in, and I attract to another person. The galaxies are constantly doing that. And if the galaxies get close and interact, the gravitational forces, you have tidal forces, things that make the gravitational pull stronger for closer and weaker for farther, starts to stretch the galaxy out. And that stretched galaxy, unless they're headed straight for each other, which what are the chances of them headed straight for each other? Pretty slim. You're going to then have them rotate around each other and spread out and make those spiral arms. It sounds really good on paper, and then when you put it in the computer and model it, computer models say, yeah, that's exactly what will happen. So scientists are pretty confident that that's what occurs to make spiral galaxies. Another piece of information that's not up here to make them confident that this is what causes spiral galaxies. Observations show that we have clusters of galaxies. So we are in a local group as part of a Virgo group and so on, clusters of galaxies. And if you have a poor cluster of galaxies, a poor cluster doesn't have too many galaxies. If you don't have too many galaxies in the cluster, you're not going to have too many collisions. A rich cluster has lots of galaxies and you'll have lots of collisions. Well, when they examine the types of galaxies in poor clusters versus rich, poor clusters have a lot of the irregular type galaxies, and the rich clusters have more spirals and elliptical galaxies. And so the belief is that basically all galaxies probably start out as clouds again, as big flocculent clouds, and then interactions between galaxies make them form into spirals. And then as you have more interactions, you have more and more of your gas and dust used up to make stars, and that makes you have less of a disk component, moving you toward the elliptical that we haven't talked about yet. Because we're talking about the Milky Way galaxy. We're getting to the end of my presentation. In fact, I think this is the last slide. The missing mass. We learned, starting a long time ago, about Kepler's laws, and that one of Kepler's laws says that if you have things orbiting, the mass is proportional to the, first thing we learned was period squared is equal to semi-major axis cubed. If you use years and astronomical units and you're in the Milky Way galaxy. But then with Newton, we learned that mass was part of that proportionality. So as long as you were in the, not Milky Way galaxy, solar system. As long as you were in the solar system, the mass of the sun was the same for everything, and it worked out. But then you can use the period and the semi-major axis to calculate how much mass is involved. And so we can do that with the Milky Way galaxy. And that blue line, it says down there below that it's what it would look like if all the matter were located inside a radius of 30,000 years. Basically, the blue line matches all of the matter we see in the Milky Way galaxy. And so we should have the orbital velocity of stars that are far out, like 25 kiloparsecs from the center of the Milky Way galaxy, having slower and slower speeds following that blue line, because the amount of mass that should be added out there is virtually none. But what's observed with those different stars is the red line. That red line means that there's a lot more mass out there than we're finding. And so that's the first indication of missing mass. And in astronomy, somebody decided in their wisdom, we're going to call that dark matter. Dark because if it was bright, we'd see it. So dark matter is a name for matter that we can't find. Now, I did mention earlier, didn't I? What percentage of matter do we actually know about? 4%. And about 20% of the matter in the universe is dark matter, and 70-some% is dark energy. We're really oblivious, it appears, to most of what's out there. But this was the first hint that we're missing something. And yes, that was the last slide. Have an excellent vacation. No, there won't be any homework for Wednesday when you get back.
Yes. Thank you. Awesome.
I hit hide instead of stop. And that admission is going to just show up on